Hi, hello everyone. Thanks for the invitation, Peter and Rose, to speak here, and also for organizing this nice colloquium. I'm actually myself in a department where I don't have that many direct mathematical colleagues who know a bit in detail what I'm working on. So this is really, I mean, even though it's not the nicest times, it's really nice that I can now have weekly seminars and things that I find interesting. Without having to travel half the country for it. So I hope some of it will still exist after we are allowed to go outside again. But I also hope that we can, meet each other in person in a while, and also go to the pub afterwards, because I heard that great ideas start in the pub, right? So I'm going to talk to you about q-analogues in combinatorics, which is a bit of a broad term. I'm going to specifically talk about the q-analog of a Matroid, of course. But I also want to sort of give you an idea of what q-analogues do, and what are some of the things that are hard and some of the things that are very pretty. So for me, I was struggling a bit with this q-analog for reasons I will go into for a bit. And then I was at one of the Sigma meetings in Eindhoven in 2016. It was actually my first Sigma meeting. And there I met Henry Crepo, who unfortunately passed away last year. But I found out that he had already worked on Q-Matroids, which he gave a completely different term that you wouldn't recognize as a Q-Matroid. But he worked on that in his thesis in 1964. But as it goes with PhD theses, people tend to forget about them a bit. And so we were actually both very happy that we run into someone who was doing the same stuff as we did. So some of the work I will present here is based on joint work with Henry and with some other people, but I will get into that. So I will start with explaining to you what I mean with a q-analog. Well, there's not really a precise definition, but what you have to keep in mind is that we go from finite sets to finite dimensional vector spaces over a finite field. And so everything you do with sets and counting things, you're now going to do it in finite spaces. So for example, if we look at the binomial coefficients n over k, it counts the number of sets of size k that are contained in a given set of size n. If I wanted to check the q-analog of that, you get the Gaussian binomial, or sometimes called the q-binomial, and it counts the number of k-dimensional subspaces inside a given n-dimensional vector space. And of course, our space needs to be over a finite field, because otherwise this counting doesn't really make sense. A bit more precise, we can use the following sort of dictionary between the set case and the q-analog. So on the left, you see all these terms in terms of the underlying lattice. And the underlying lattice for sets is the Boolean lattice. So you take a set and all its subspaces and they form a lattice. We call that the Boolean lattice. And for a finite space and all its subspaces, we get a lattice that we simply call the subspace lattice. Now, if we're talking about elements of a set, then the q-analog of that will be the one-dimensional subspaces of a subspace lattice. If we talk about the size of a set, the q-analog of that is the dimension of a space. The number, the natural number n, it also has a q-analog, because it's actually the number of elements, the number of atoms that are in your lattice. So if I have a set of size n, then I have n atoms. And if I have a space of dimension n, then the number of one-dimensional subspace is q to the n minus 1 over q minus 1. So that's exactly the number that you see over here. Can you see me pointing, by the way? Good. Okay. The meat in this lattice, for the Boolean lattice, it's the intersection, and also for a subspace, we can talk about the intersection. And what is the union for sets becomes the sum of subspaces. So the change that we're going to make is we're not going to do things with the Boolean lattice, but we are going to do things with the subspace lattice. You can say that if we go from the q analog to like the normal case, you let q go to 1. And that's just a fancy way of saying that set theory is actually projective geometry over the field with one element. Of course, there's no field with one element, but we can still do geometry over it, and it's just sets. So the first thing that you can do if you want to go into q-analogues is just stare at the definition and make a straightforward q-analog of it and see what falls out. Well, that's what we did with Matroids. So here's your definition of a q-matroid. It consists of a pair E and R, where E now is not a finite set, but a finite dimensional vector space. And I have a rank function that is a function that associates to every subspace of E a number, its rank. And its rank has 3 properties. The rank is always between 0 and the dimension of the space. And this dimension is the q-analog of the size of a set. We have that if A is inside B, then the rank of A is smaller than or equal than the rank of B. And we have this semi-modular inequality, where we have to watch out that the union is replaced by the sum. And it turns out that replacing a union by a sum sometimes runs us into trouble, but I will get back to that later. So this is a definition of a q-matroid, and you might wonder, well, this is nice, but you know, do these things exist? Are they actually interesting objects? I mean, you can take some more or less trivial examples. You can make a uniform q-matroid, for example, but that's not really, we don't really need a new definition just to do that. So let's see where this actually came from. Where this came from for me was when I was working with Ruud Pellikaan, my PhD supervisor. I had worked in my PhD on the relation between matroids and linear codes. And around the time that I was finishing my PhD in coding theory, the next big thing was rank metric codes and actually network coding. And this can be viewed in a certain way as a q-analog of normal coding. And so we said, oh, well, these nice relations that I did in my PhD thesis, maybe we can make a q-analog of it. And for that reason, we needed the q-analog of a matroid. And the good thing is that these rank metric codes, I'm not going to tell you in detail what they are, but they are examples of q-matroids. Well, how does that work? Again, I'm not going to tell you exactly what is a linear rank metric code, but you can remember that it can be generated by a matrix, and this matrix is a matrix over an extension field. So the entries of G here, they are in FQ to the n. That might feel a bit strange because our matroid is going to be over FQ. But what we do is we take this generator matrix, and if we want to talk about the rank of a subspace, well, of this FQ to the n, what do? We take a matrix whose columns span the subspace. That's this matrix Y here. We multiply it with this generator matrix of the code. So this is a code over an extension field. Sorry, this matrix over an extension field. This one is just over FQ. We get a matrix also over the extension field, and we look at the matrix rank of this. And it turns out that this rank actually satisfies all the axioms that I had on the previous slide. So our rank metric codes, or actually just well, matrices over an extension field, they give us examples of q-matroids. The funny thing is that if you wouldn't take any extension field here for G, then you always end up with a trivial kind of q-matroid. It won't be an interesting thing. So we really need this extension field over here. And I also want to note that this way of calculating the rank, maybe it reminds you a bit on how we calculate the rank in case of a representable matroid. right? If I have a normal Matroid that's represented by a matrix, if I multiply it by like the characteristic vector of a subset where I want to know the rank of, so I make a vector that has ones in the positions corresponding to the elements in the subset I want to know the rank of, then you also get some kind of projection. And if you take like the matrix rank over there, it is your Matroid rank as well. So there's a bit of a similarity here. So this is good news, because it means that, you know, my definition of a Q-Matroid that I sort of, you know, invented by simply generalizing my my definitions from sets to spaces, it actually leads to, I mean, we actually have examples of this that are not completely, well, trivial or boring objects. So we have now defined our Q-Matroid in terms of a rank function. But of course, one of the pretty things that that Matroids have is that you can define them in a lot of different ways, a lot of cryptomorphisms. And finding cryptomorphisms for Q-Matroids is great fun, and I will tell you a bit about why it's fun and not boring. Of course, I could have also started with saying, well, my Q-Matroid, I'm going to define it in terms of independence. I just take my regular axioms for independence, I generalize them, and I just hope that everything works out. So what am I going to do? I take E, a finite dimensional vector space, and I'm going to say some subspaces are going to be independent. The terminology is maybe a bit strange, but hey, just some of the spaces are independent, the other ones are dependent, and they have to satisfy certain properties. First, if I just take the zero vector, like the zero subspace, it needs to be independent. A subspace of an independent space is also independent. And we have that if I take two independent subspaces, and now that the dimension of one of them is bigger than the dimension of the other, then I can find something in the bigger one, to be precise, a one-dimensional subspace that I call X. And it is in the bigger one and not in the smaller one. But if I add it to the smaller one, I get something independent. So this is like a straightforward q-analog of the definition of a Matroid in terms of its independent sets. Well, and of course we want to say, well, we also had this definition in terms of the rank function, and now we say, well, the rank of something is actually the dimension of the largest independent space that is contained in A. And on the other hand, I can find all the independent spaces by taking all subspaces whose dimension is equal to their rank. Well, the bad news is that the thing you see here on the screen is not equivalent to the definition of a Q-Matroid that I showed you before. And I will go a bit in why not and how can we fix this. Well, why not? Let's start with a counterexample. So this counterexample, it is our ground space, so to say, is f2 to the 4. So we are in a binary vector space of 4 dimensions. And what we say is, well, we take this 2-dimensional vector space here. It's spanned by these two columns, by these two rows, and I take all of its subspaces. And it's not really difficult to check that this actually satisfies the axioms I had on the previous slides. So the independence axioms, and also it satisfies the first two rank axioms, but it fails semi-modularity. Well, how can we see that? Let's look at A and B over here. They are spanned by the rows that we see. So these are two 3-dimensional spaces. If I take A plus B, I get everything. Well, the largest independent space inside everything is exactly the space over here, which has dimension 2. So the rank of A plus B is equal to 2. If I take the intersection between A and B, well, I see that the last two rows of A and the first two generator rows of B are the same. So what do I get? Inside, I get the vector 1, 0, 0, 1, which is something independent. We don't have something bigger that is independent. But we see that the intersection between A and B actually has rank 1. Now, what's the case with A and B themselves? Well, this completely two-dimensional subspace is not contained in either A or B, but this vector 1, 0, 0, 1 is contained in A, it's also contained in B. So both of them actually have rank 1. But this is a problem. This contradicts semi-modularity. And where does this contradiction show up? Well, the problem is actually in this plus that we have here. Because something strange happens. Because in A and B, both A and B don't contain the vector 1, 0, 0, 1. But if I add them together, then they will contain this vector. And so also the one-dimensional vector space that it spans. And this is causing problems. And you see that in general with the sum in subspaces, if you mirror it versus the union in sets. If you take the union of two sets, then you get all the things that were either in A or in B and nothing else. On the other hand, if I take the sum of a space A and a space B, I get a lot of stuff that was either in A or in B and a lot of other things, right? Because, you know, everything has to be a linear space. So you get a lot of extra, well, one-dimensional spaces and more dimensional spaces. And this is something that you have to take care of. And that's one of the difficult things that you encounter a lot in making q-analogues, that as soon as there is a sum, or as soon as there is a union somewhere in the set case, in the q-analog, you alarm bells will go off because it doesn't really behave that nicely. So we now have a problem, and we can actually show that these rank axioms that we had, that they imply the independence axioms, but it doesn't go the other way around. And the solution Ruud and I agreed on was to find an extra axiom for independence. There are a few things to say about why we would need something like that. First is a lemma that follows quite easily from semi-modularity. And that is, if I have a one-dimensional space of rank 0, that's a loop, and I have another loop, and I add them together, then I shouldn't get something of rank 1. If I have something of rank 0 and another thing of rank 0, if I glue them together, then it should still be rank 0. And so actually loops come in subspaces. If I look at all the one-dimensional spaces that are loops, they have to form one whole subspace. I can't have things like that sticking out. And that's actually the thing that's going wrong in the example. If I have an axiom set, and this is the corollary here, if I have some axiom set that's invariant under embedding my ground space in a bigger space, then that's not enough. Because if I go back to the example, well, what you see here, this I that I have constructed, well, what is this in disguise? It's just the complete free Metroid in 2 dimensions that I have embedded in 4 dimensions, right? I take something of dimension 2 and it's independent, and everything inside it, it's independent. If this were a 2-dimensional subspace, I wouldn't have a problem. But now I embed it in a 4-dimensional subspace and all of a sudden things go wrong. So that's annoying. Because my axioms for independence, they sort of are invariant under this embedding stuff. But it turns out that they shouldn't be. So I won't go in all the details of the proof because it's a bit tedious. And we ended up with this extra axiom, which is, well, still not a very pretty thing, but at least it makes everything work. And it says, if I have 2 subspaces, and I take inside I and J to be the maximal independent subspaces inside A and B, then there is a maximal independent subspace of A plus B that is contained in I plus J. So that means that if I take A and B and I glue them together, then the maximum independent stuff that I get should be inside something that was already independent in there. The interesting thing is that the classical version, the set version of this axiom I4, it's you can just prove it from the other three. You don't need this extra thing. But in the q-analog, you do need it because it gives you the amount of information that you need in order to use all these things to make semi-modularity of the rank function work. And well, I don't think it's a particularly pretty thing, but if you just spill out the whole proof of trying to get the rank axioms from the independence axioms, at some point it goes wrong, and if you assume this, everything will go right. And then of course you have to prove that this holds assuming the rank axioms. So the interesting thing also to realize is that if you take two cryptomorphic definitions of a Matroid and you take q-analogues of those, they might end up not being cryptomorphic anymore. This is a general thing for q-analogues. You can take two things that are equivalent for sets, and then you take the q-analog and you get something that's not equivalent anymore. Well, let's focus a bit on the reason why this is. And the reason why this is has to do with distributivity of a lattice. We call a lattice distributive if the join and the meet satisfy the following two formulas. And what they actually just mean is like distributivity for adding and multiplying, right? If my join was plus and this was a times, and then you get the well-known thing that you can just multiply x with z and then plus y times z, but then in a lattice. And the thing is that the Boolean lattice is distributive, but the subspace lattice is not. And if we just stare at the first line, assume that x, y, and z are one-dimensional spaces, and z is in the span of x plus y. Then what do we have here? Well, x join y is x plus y. If I intersect that with z, I get back z, right? Because I assumed that z was in this span. But on the right-hand side, the intersection of x and z is just 0. The intersection of y and z is also 0 because I assumed they were distinct one-dimensional subspaces. And so also if I add them together, if I add 0 and 0, I still have 0. So I have something one-dimensional on one side and something zero-dimensional on the other side. So, and you see that it's exactly this join, like the plus in subspaces, that is causing trouble here. Well, it wasn't really me who realized that this is the thing that's causing trouble. So I want to give you a fabulous quote from a paper I found from Chen and Rota in '92. It's long, but I'm just going to read the whole of it for you. The fact that joins and meets in a lattice of subspaces does not satisfy the distributive law that holds for union and intersection of sets was once seen as a fatal drawback. Recent work on q-analogues of some deep enumerative properties of finite sets has shown such fear to be groundless. So far, every combinatorial property pertaining to subsets of finite sets has eventually been absconded in the more rarefied but more refreshing air of vector spaces. The proofs of the q-analogues of combinatorial properties of finite sets are often far more difficult, but they are more rewarding in that they often display features of the problem that were invisible in dealing with sets. Thus, the failure of the distributive law of set theory has proved to be a purely psychological obstacle, at least as far as enumeration goes. I think this is a brilliant quote. I mean, I think nowadays I wouldn't even dream of writing something like this in my introduction, but I think it really encaptures some of the problems and also some of the maybe slightly naive ideas that we can overcome all the problems. I do like that the arrow vector spaces is more refreshing. And I also think there is a point in the fact that the proofs are more difficult, but also once you have, once you have find the q-analog of something, you sort of have to pinpoint down what is exactly the thing from sets that you want to generalize to spaces. And often in sets, there's a lot of things that are all equivalent, and you just don't mind because they're all equivalent. And then in the q-analog, you sort of have to find the right way to state your problem, and then the q-analog just drops out. But sometimes if you're stuck with like a wrong description of your problem, then you will get nowhere with the q-analog. So I can really feel what Chen and Rhoda are trying to say here. So I now want to go a bit more into this underlying lattice thing and how you can use it to view matroids. And this is actually the way to view q-matroids that Henry Crapo was working on. And I will explain it to you by example. So here is a classical matroid. It's a matroid on 4 points. I made the picture here. I have 2 parallel points, B and C, and the other ones are independent, and it's a matroid of rank 3. Well, I can make a visualization of this matroid by coloring the Boolean lattice on 4 elements. So I have made here all the subsets of the set of 4 elements, and I've neatly ordered them in the Boolean lattice. And now what I'm going to do is all the covers, I'm going to color them red if the rank goes up, by going to the next element, and I make them green if the rank stays the same. So instead of coloring, you could also put in 0s and 1s, but coloring just looks better. And you can see that indeed this is a matroid of rank 3, because any route I take from below all to the top, it will have 3 red and 1 green line on the way. And the number of red lines is the rank. And also you see, for example, that BC are parallel points. So B and C are independent, but BC is dependent. So if I go from B to BC, the rank stays the same. So this is a green cover. And if I go from CD to BCD, also the rank stays the same because I'm only adding B, which is not really doing something for the rank. And so this also is green. Most of the others are red because the rank is going up. Now, it turns out that you can say when is a coloring of the subspace lattice a matroid. You can say that by the following, well, let's just call it a cryptomorphism. A coloring is a matroid if and only if you have only the following diamonds. And a diamond means like an interval of length 2. So that means there's 2 things in between. And we have 4 covers to color. Then either everything is red, so you can see it as 2 independent things that together also form something independent. Everything can be 0, so you like have all loops. It can be of rank 1 and mixed, or it can be of rank 1 and it's prime. So you first have 2 independent things, but they are dependent of each other. The only thing that you can't have is green below and red on top, because that would mean 2 loops adding up to something of rank 1. And we can't have that. Now, for a q-matroid, it turns out you can do something similar. If you look at all the diamonds, well, in a sense they look more like diamonds, but that depends on how you think a diamond should look. If you take the intervals of height 2, then either everything is colored red, everything is colored green. You can have all red below and then a green on top. But the interesting thing arises with the mixed one over here, Because if we have one green line here, that's like the maximum number of green lines that you can have before everything becomes 0. So you can't have 2 green lines below, because that would mean that I have 2 loops. And we saw that loops come in subspaces. So as soon as I have 2 loops, then everything that they span should all have rank 0. And so if I put 2 green covers on the bottom, the only thing I can end up with, so the only way to color the rest of it, is to make it completely 0. So again, you just have one mixed diamond. And the interesting thing is that we saw before these independent axioms, they actually wouldn't exclude the mixed diamond that has more green lines below. But you can show that this, so these 4 things, they actually imply the rank axioms for the q-Metroid and also the other way around. Well, let's see some examples of how these q-Metroids look. So here's one q-Metroid of rank 1. It is over the 3-dimension binary field. And well, instead of 1-dimensional subspaces and 2-dimensional subspaces, we can think projectively about the points and the lines of the Fano plane. The coordinates are the Plucker coordinates here. And you see that 3 points, who actually are on one line, they are loops. And the other 4 points are independent. And then you sort of color the rest green and red such that everything works. So if you take, for example, the diamond between here and here below, we have a mixed one because we have 2 greens and a red one on top, and we have this one green and then 2 red ones below. So that's a mixed interval. We can also see, for example, from here to the top, it's all zeros, it's all green. We don't have one that's all ones because the thing only has rank 1. And I think you can also find, no, I can't. Let's go to my next example because that actually has diamonds that are completely red. Now we don't have ones that are completely green because of the nullity is not high enough for that. And you see that, for example, here, this interval, it's a prime because we have all red below and then green on top. And it turns out that there's not that many Metroids possible. I mean, this way of coloring it, it's really a restrictive thing. You would say, okay, I have so many more things to color than I have in the set case, but you fill up your diamonds pretty quickly. Good. So this was the status about a year ago, and last summer I was at a conference in France. It was called Women in Numbers, the European chapter, part 3. And it was a conference where they would before make projects and project groups where these groups would start working together on a common problem. So Emer Beern, who you see here, she asked me to join her in coming up with a project, and we came up with q-analogues in Combinatorics. And we were joined by 3 other members. Here's Elif Sisakara, who is a postdoc in Zurich. There is Soria Ionica, who is at Université Picardie. And there's Michela Siria, who is now a postdoc in Milan and is actually looking for a job, so hire her. And we started working on q-analogues in Combinatorics, and so, of course, the q-analogues of Metroids, but also a bit in coding theory and in designs. And this last thing I want to tell you a bit more about. So if you were a bit lost in all the Metroids, I'm now going to talk about designs. What is a combinatorial design? It's a thing that has a lot of parameters, t, v, k, and lambda. But what it is, it's a finite set with v elements, and we call them points. And then we take some subsets that all have the same size, k, and we call them blocks. And the thing now is that every t-tuple of points of the big set is contained in exactly lambda blocks. So this feels a bit like how you would also define a Matroid, right? You have a set and you have certain subsets and they satisfy some nice property. That's also what you do here. Designs where lambda is equal to 1, they are special and we call them Steiner systems. Because then you can say that every t-tuple of points is contained in exactly one block. And it turns out that this is a lot harder than saying that they are in multiple blocks. An example of a design is the Fano plane. You take 7 elements, the 7 points of the Fano plane. You say that the blocks are lines. They all have size 3. That's the 3 over here. And we have 7 points. And you can say that every pair of points, so every 2 points, they are in exactly one line. So the Fano plane and in fact every projective space is going to give you a design and actually a Steiner system. Now, Matroids also have something to do with designs by means of something that's called a perfect Matroid design, which is a very strange name because it's a Matroid and not a design. But it's a Matroid where all the flats that have the same rank also have the same size. Well, there are 4 known classes of perfect Matroid designs. First, we have the projective spaces, like the Fano plane we already saw. In fact, if you just take the flats in the geometry as the flats of the Matroid, then you get that all the flats have the same number of points on them. And if you truncate them, it will still be a perfect Matroid design. You get the same thing for affine spaces. You also get Steiner systems. So these are the designs I just talked about, but with this special property that every t-tuple was in exactly one of the blocks. And the fourth one, they are called triffics. They come from finite commutative Moufang loops. I don't know what any of these words mean, so please don't ask me about it, or explain them to me if you do know about them. So these perfect Matroid designs, they can be used to produce designs. And this is quite an old statement by Murty, Young, and Edmonds. And they say, given a perfect Matroid design, we can make the following designs. We can take all flats of a given cardinality and we say, this is the set of blocks of a design. Or we can say we take all independent sets of a certain cardinality, and these also form the blocks of a design. And the same thing holds for the circuits. Well, what we wanted to do with our wine group was to find a q-analog of this theorem. Because what's the nice thing of this theorem? It actually uses from this PMD the Matroid structure in order to get a design. Well, for that to do, we of course need to talk about the q-analog of a perfect Matroid design. And for that, we first need the q-analog of a design. This thing is called a subspace design, and it gets another parameter added, which is now the size of the field. And its definition is exactly as what you would think it is. Instead of a finite set, we now have a finite vector space of dimension v. We take a family of k-dimensional subspaces. These are the blocks. And we say that every t-dimension subspace of X is contained in exactly lambda blocks of B. And again, if lambda is equal to 1, these things are called q-Steiner systems. Now, subspace designs are quite rare. A sort of easy example is if you take both t and lambda equal to 1, then you get a spread. And because what you then get is you say I have a space and I take a number of k-dimensional subspaces in such a way that every one-dimensional subspace is in exactly one of the blocks. So it's sort of a partition of the space. And partitions of spaces are called spread. And for a long time, it was thought that this was like the only example that we had for lambda is 1, so for this Q-Steiner system. I mean, people had found subspace designs for bigger lambda, but for lambda is equal to 1, they somehow only also had t equal to 1. So this example with the spread, and it's a bit boring. I mean, we know what spreads are and when they exist and stuff like that. But then, I mean, subspace designs were also invented like in the 80s, but they became in fashion also because of ranked Metroid coding over the last decade. And people started looking for more subspace designs. And actually in 2014, there was a non-trivial Q-Steiner system found, and it has parameters 13, 3, 1, 2. So that means you take a binary 13-dimensional space, and you take some of the 3-dimensional spaces that are blocks in such a way that every 2-dimensional space in this big 13-dimensional space is contained in exactly one of the 3-dimensional spaces. And the thing is, this is like the only example that we have of non-trivial q-Steiner systems, which is slightly embarrassing because we also have some extreme combinatorics proofs that they should exist for more or less every parameter set that's admissible that you want. And the smallest set of parameters, well, that could be a parameter set is the q-analog of the Fano plane. And we don't know if it exists. So it's a 7-dimensional space, and you have to give some 3-dimensional spaces in such a way that every 2-dimensional space is exactly one 3-dimensional space. For the binary case, you can calculate how many blocks it has. It has already 381 blocks. That's a lot more than the 7 blocks for the set case. So here you see that q-analogues, the numbers, they blow up immensely. So you can't really put this thing in a computer. I mean, people try to do that, but usually with this big combinatorial structures, in a computer search, what people do is they say, well, assume my object has a large automorphism group. Then I mod out my search space by this automorphism group. And then I have fewer space to look at. And if I'm lucky, I find my object. And if I'm unlucky, I know that it doesn't exist with my presumed automorphism group. So that's actually how they find this design. It just has a big automorphism group. And they found this by computer search. We know that the q-analog of the Fano plane in the binary case, it either has no automorphism, so it's rigid, or its automorphism group is of order 2. So we narrowed it down, but then the search became so big that we didn't finish it. We do, by the way, have a construction of this, but then over the real numbers, using octonions. And it's really pretty, but you can't really count anything from it. So it depends on which side of the mathematical world you come from, if you like that or not. So this is a bit on this non-trivial q-Steiner systems. We have one of them, but we do hope that, just as in the set case, it gives us perfect Matroid designs, or actually the q-analog of that. Well, it's not very difficult to define a q-PMD. It's just a q-Matroid where all the flats of the same rank have also the same dimension. And you can show that q-Steiner systems are in fact examples of these q-PMDs, where the blocks are the maximum proper flats of this q-PMD. So again, making the definition is kind of easy. You just take the q-analog of something that you already know, and then you have to find an example of it, and you're happy if you find it, because then at least the thing you defined, it sort of made sense. It was not an empty definition. Well, in order to prove that these q-Steiner systems are q-PMDs, we wanted to reason a bit about the flats of a q-Matroid. So one of the things we did in our recent paper is we found a cryptomorphism for a q-Matroid in terms of flats. And the thing is, it looks exactly as you would think it looks. So this is not a very surprising theorem, but you know, we did need to do some work to prove it anyway. The flats of a q-matroid, they are defined by these three axioms. First of all, everything has to be a flat. The intersection of two flats needs to be a flat. And the third one, maybe it looks a bit different from the statement that's commonly used. It says if I have a flat and I have a one-dimensional subspace outside the flat, then there is a unique flat f prime that contains x and it contains f, and it's actually a cover of f. So that means that there's no flats in between f and f prime. And this is the same thing as saying if I take all the flats covering f, they partition everything that's left. But you sort of have to say it in the right way for the q-analog to make sense. Well, once you have this, you can reason away with showing that q-Steiner systems give q-PMDs. And we also proved the q-analog of the theorem you saw before. Unfortunately, we were only able to prove it like exactly for a q-Steiner system and not a q-PMD in general. We still don't know if other q-PMDs exist, of course, but you know, it would be nice to have a more general version of this theorem, but we have it for this one example that we have. It says that if I take all flats of a given dimension, we get a design. If I take all the independent spaces of a given dimension, I get a design. And the same thing for the circuits. Now, it sounds maybe a bit strange that you come up with all this Metroid theory stuff, when in the end what you do is you start with a design, a Steiner system, and the result that you get is also a design. But we are actually using the Metroid structure of this q-Steiner system in order to get to this second design. And the fact that this theorem really adds something is demonstrated by the fact that we found a new design. So this only non-trivial q-Steiner system that we had, we plugged it in our theorem, and the parameters that came out of it were parameters that were not known to hold a subspace design. So we found a new one. So it definitely helps if you view your q-Steiner system as a q-PMD, because this Metroid structure actually helps you in finding new designs. Yeah, so this was a nice bit of mathematics coming from Metroids and other things, and that was actually where I wanted to end. So I end with a pretty picture. This is the view from my office. And thanks for your attention.
Thank you very much, Relinde. Are there any questions? Then
I have a question. So over the time, there have been several attempts at generalizing Metroids from this lattice of subsets to various other lattices. Have you checked whether some of them is similar to yours?
Well, I don't know about a lot of them. I know that Relinde, he made a generalization to something that he called quantum Metroids.
Oh, that's not one I know.
Yeah, well, the interesting thing is that, one of the examples of this quantum Metroids are actually Metroids that have these three independent axioms that I said were not enough for a q-Metroid. So, so that's one of the things I knew. And the other one, I mean, I know of Crapo's work. And so you can generalize, so this thing that we did with the coloring, you can generalize it not just to the subspace lattice, but you can also generalize it to every complemented modular lattice, if I'm not mistaken. So there are other kinds of lattices where the same thing holds, and you can also say, well, my coloring has to satisfy, well, only some of these diamonds, and then you also get a definition of something that's, well, feels a bit like a Q-Matroid.
Interesting. None of these two generalizations were amongst the generalizations I knew.
Okay, so please tell me about that.
So one is the notion of super Metroids, and it appears in a little section in Welsh's book. The original source I am not able to find. They're defined to be on any poset, but I think the only results are on like submodular lattices. Sorry, semi-modular lattices.
Are you thinking about Ulrich Feigler's work?
Sorry, about whose work?
Ulrich Feigler.
Sorry, I don't understand the name.
It's
Ulrich Feigler.
F-A-I-G.
No, the reference is to Dunstan, Ingleton, and Welsh, but the paper I cannot find.
Yeah, but I'm talking about something else.
Ah,
Matroid-like stuff on posets. I vaguely remember this.
oh, I think I've also seen this Feigler geometries and partially ordered sets, right?
Probably, that sounds right.
That's another thing I've not told you about.
Can you spell the name again for me? Fei?
F-A-I-G-L-E.
Yeah.
He actually was in Twente for quite a while.
Okay.
All right, are there any other questions? I've got one question then, which is possibly covered by the previous one to a large extent, but how much of your cryptomorphism works if I just told you I was assigning ranks to flats in the lattice of flats of a Matroid? So like a Matroid on a Matroid. You know what I mean?
Yeah. Well, it's not, so at least this thing is in general not modular, right?
Mm-hmm.
So most of the things I work with, and especially the things I work on with Henry, they really need to have something modular, because otherwise you can't. It's difficult to make your rank function well defined, right? Because you somehow have to say that every chain from a point to another point contains the same number of red and green lines. So making a Matroid on a Matroid, I think this will be a hard property to satisfy.
Well, you almost get nothing. You'll just get the projective geometries, which are your Q-Matroids, and also maybe regular Matroids. Matroids in the usual sense. Yeah. Okay.
So the interesting thing maybe to mention is that you can talk about the flats of a Q-Matroid, and they actually do form a geometric lattice. So they give a Matroid back. Mm-hmm. But unless with classical Matroids, normal Matroids, they don't contain all the information on the Q-Matroid. So you can have different Q-Matroids that sort of project down to the same lattice of flats.
Oh, so there is no cryptomorphism there, or is it just the lattice forgets it?
Well, no. So there is a cryptomorphism for the flats, but if you would say I'm only going to take the flats. Well, I have to say this the right way.
You mean the abstract lattice is not enough?
Yes. Yeah. So the lattice of flats is not enough to define your Q-Matroid. You at least have to come up with, for example, because if you only have the lattice, you have, for example, not the underlying space.
Yeah.
And the field, right? So.
Okay, but that's not surprising.
No.
I wouldn't expect it to be enough. Let me say it this way.
Yeah.
But if I know what spaces the flats are, that's enough, right?
Yeah, I think that's enough. Yeah, because then you just know what is your ground space, and you have all the flats, and that's the statement we proved. Then you the flats, they completely determine your Matroid, but you have to know what it is the Matroid. So not just their lattice structure, but actually which spaces they are.
Are there any other questions? If not, we can thank Relinde again for that fantastic talk. Thank you.